All right, so we left off on number 6. Told us the focal length, it told us the height of the object, it told us the distance the object was from the mirror. It asked us to find DI in part A, where the image was located. So 1 over F is equal to 1 over DO plus 1 over DI. So 1 over DI is equal to 1 over F minus 1 over DO. So 1 over 9 centimeters minus 1 over 6 centimeters. Common denominator is 54. So 6 over 54 centimeters minus 9 over 54 centimeters gives you a negative 3 over 54 centimeters. So DI equals negative 54 centimeters over 3. So what is that? DI is equal to negative 118, maybe? Did I do that right? Not here to tell me. It is 18. 18 centimeters, where again the negative means virtual. Okay, and then it asks us to find its height. So, hi-ho, di-do, off to work we go. Okay, so HI will be equal to negative DIHO over DO. So negative, negative. And the HO they told us was 15 millimeters. And over 6 centimeters. So HI, the negative, negative becomes positive, and I think we get 45 millimeters here, right? It goes into 3 times, yeah. All right, so that was number 6. Number 7. Number 7 says, a 4 centimeter high candle is placed 10 centimeters from a concave mirror. So HO is 4 centimeters, and it's placed DO 10 centimeters from a concave mirror, having a focal length of 16 centimeters. And so again, the question wants us to find the DI and the HI. So 1 over F is equal to 1 over DO plus 1 over DI. So 1 over DI is equal to 1 over F minus 1 over DO. 1 over 16 minus 1 over 10. Lowest common denominator would be 80. So 5 over 80 minus 8 over 80 would be negative 3 over 80. So DI is equal to negative 80 over 3. So negative 226.6 repeating, where the negative means virtual. Okay, and then the HI, so hi-ho, hi-di-do, and then put your negative in. So HI will equal negative DIHO over DO. So negative 26 2/3 centimeters times 4 centimeters over 10 centimeters. I really don't want to do this one in my head. Wait, that'll be 2 over 5, so 252, 53 1/3. Ugh, I don't know what it is. I could just punch it in my calculator, couldn't I? Does it get... So 26 2/3 times 4 divided by 10. 10 2/3. Oh, I should have been able to get that. And it's centimeters this time. Okay? And then the last one is, what should be the radius of curvature if a concave mirror that magnifies an object placed 25 centimeters from the mirror by a factor of 3? All right. So in the end, we're looking for R, but it means we need to find F. And it says it magnifies the object by a factor of positive 3. And it says that the object is placed 25 centimeters from the mirror. So DO is 25 centimeters. Okay, so the first step would be to find di. So m equals negative di over do. So di is going to equal negative m times do. So negative 3 times 25 centimeters. So di is going to equal negative 75 centimeters. And then go to 1 over f is equal to 1 over do plus 1 over di. So 1 over, what was do? 25 centimeters plus 1 over negative 75. So 1 over f is equal to 3 over 75 minus 1 over 75, which is equal to 2 over 75. So f is equal to 75 centimeters over 2, or 37.5 centimeters, which means r is equal to 2f, or 75 centimeters. Okay? So those are all your homework questions. So hopefully they were okay. And hopefully you're getting a hang of the negative. Now, speaking of the negative, oh, actually I could use the back of that sheet. It's time to look at the second type of lenses, which are second type of mirrors, which are convex mirrors. And you'll understand in a second why I said speaking of the negative. So a convex mirror is a mirror whose reflecting side bulges out. So this is the reflecting side here. And the F is going to be back here. And so's the C. But this is the reflecting side, so this is the real side. This is where the object's going to be placed. And so the F and the C are going to be virtual. Okay? So whenever you get a convex mirror, when you're putting the focal length in an equation, it's going to be virtual. Really, there are two rays that we use. We use a ray that is going in parallel to the principal axis, but it's not going to be able to get reflected through F, because F is down here. So it's going to get reflected in such a way that it appears to be coming from F. So it's going to get reflected off like this. Okay? And then the second ray that we'll use will be a ray that it can't actually go through C, but it's going to appear to pass through C. And if it appears, maybe this one's actually appearing to pass, I didn't do a very good line here. Appears to pass through C, will get reflected back on itself. Okay? And where they cross, that's where the image will be. Okay, so there were two rays. One going in parallel to the principal axis will get reflected in such a way that it'll appear to come from F, and one that appears to pass through C on the opposite side of the mirror will get reflected back on itself. Before we get to the one case, here's F. This type of mirror is called a diverging mirror. And it's called a diverging mirror because rays that go in parallel to the principal axis from the top and from the bottom will appear to come from F, but will really end up diverging on the real side. So that's why it's called a diverging mirror. We had one case over here to do. So we're going to put our object outside here anywhere. And we're going to do a ray coming from the top in parallel to the principal axis. We'll go out so that it looks like it's coming from F. And a ray coming in through C. And this one's really hard to do. Will go out will get reflected in such a way that it will go back through C. From the bottom, a ray going in parallel to the,